Hi, good morning, good afternoon, or good evening, and welcome to our virtual poster. My name is Sofia Bravo, and I'm a PhD student in Schulz Lab in the Ruhr University of Bochum in Germany. Today, I will talk about Streptomyces cinnamonensis metabolomics. Streptomyces are the richest sources of antibiotics in the whole world, and Streptomyces cinnamonensis is not an exception. It produces the antibiotic monensin. Monensin is synthesized by the type 1 Polyketide Synthase. This is actually comprised by 8 different separate multi-enzyme complexes. Each one of these complexes has conserved domains that are responsible for assembling the different precursors into the backchain of the molecule, similar to an assembly line each one of these has a specific task. Individual modules can be mutated or exchanged easily to create the molecule of your choice, or even you can create a library of bioactive compounds. The problem is that this genetically modified strepto produce low yields of molecules. A few decades ago, a monensin overproducer was created by random mutagenesis, but up till date, it's not completely understood how these or other related strains can affect the antibiotic titers. Our goal is then to see which are the genetic changes between the wild type and the overproducer and other mutated strains. And because there's so many genetic changes, we're going to use metabolomics. Metabolomics is indispensable to see which are actually the genetic changes that are indispensable for producing these monensin high titers. To answer our question, we started from liquid cultures, then we quench them using alcohol-based solvents, we lyse the cells using freeze-thaw, and from these with different solvents of different polarities, we extracted different fractions. Each individual fraction was freeze-dried, reconstituted, and measured via LC-MS using reverse phase or Heilig, depending on the polarities of the compounds, of course. Data analysis was performed using data analysis and metaboscape from Bruker, or in the case of untargeted, we use MZ-MIND3 for the pre-processing steps and Metaboanalysis 5 for the statistics. The annotation of the compounds was assessed with Sirius 5 and with feature-based molecular network by GMPS. We created a library of monensin derivatives by making targeted mutations on the different keto reductase modules. We did a targeted approach, so we did the extraction of the hop of key intermediates of the monensin biosynthesis, and we analyzed them via LC-MS. We found out that there was an accumulation of the biosynthetic intermediates in the mutated module and downstream. This shows that the reduced catalytic efficiency and the drop in yield is due to a substrate specificity in downstream modules. In other words, targeted metabolomics seems to be a great way to identify bottlenecks in different mutated strains. Right now, we are working to expand our work to untargeted, to see up and down regulated pathways not only in secondary metabolism, but also in primary metabolism. I hope you enjoyed my presentation, and I hope to see you soon. Bye!